Alright, welcome. This is Module 13, Chapter 10. There's actually just one part to this video. And so we're really going to be talking about gases. We've been looking at the microscopic view of molecules and ionic substances, but we don't actually have any direct experience with atoms, right? We don't actually encounter atoms where we can see them. We encounter matter as either a gas, a liquid, or a solid that are composed of numerous atoms or molecules. So Chapter 10 really focuses on the physical properties of gases and its behavior. And if you take General Chemistry 2, you'll really start off the class with liquids and solids. So basically all substances have three phases. We have solids, we have liquids, and gases. Okay? And so substances that are liquids or solids under ordinary conditions can also exist in a gaseous state, okay, which we call vapors. And there's a lot of properties that make up a substance, or make a substance a gas. And so gases really are just one of the easiest forms to understand. The chemical properties of gases may differ, but the behavior is similar as far as the physical properties are concerned. Right. All gases are composed of nonmetals. They have simple molecular formulas, and they have very low molar masses. When we talk about gas molecules, they're usually very far apart. Okay, so in a given volume of air, the molecules only take up about 0.1% of that total volume that it's contained in. So gas molecules act like they are alone and that there's no other molecules present. Okay, so really gases just occupy a small fraction of the overall container. Well, a gas can exert a force on any surface which they are in contact with. So pressure is a force that acts on a given area. Okay? Thus we can define pressure is equal to the force divided by the area. Okay? So the SI unit of force is called the Newton, okay, which is equal to 1 kilogram meter per second squared. The SI unit for area is going to be meter squared, and the SI unit of pressure is called the Pascal. Okay, and 1 Pascal is equal to 1 Newton per meter squared. Okay. Well, if we know the mass and acceleration of a particle, then we can actually determine the force of that particle as well. Okay, and so we should be familiar with these other units of pressure. I will give you these on an exam. I don't expect you to know them. The one thing I do expect you to know is that 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr. Okay, that one's important for you to know. Now you should also be aware that gravitational forces are also experienced by gas atoms and molecules. So if you think of the atmosphere, right, the gravitational force is pressing down on the Earth's surface, resulting in what we call atmospheric pressure. So the next question that should come up is, well, how do we measure the pressure of a gas experimentally? Okay, well, there's a couple ways. One, we can use a barometer or a manometer. Okay. And when we're talking about a barometer basically just has this glass tube, okay, which is more than 760 millimeters long, and it's closed at this top end, okay. Basically, the tube is filled with mercury, and then it's inverted into a bath filled with mercury, okay. And as it's inverted, mercury is going to flow out of this tube into the bath, okay. Well, the atmospheric pressure that's being pushed down on this bath of mercury, okay, will push mercury back up into the tube until the gravitational force is equal to the atmospheric pressure. Okay? So if we measure the height of this mercury, okay, then we have actually determined the atmospheric pressure. Okay? So it's a pretty basic idea, but it actually works very well. The standard atmospheric pressure is 760 millimeters of mercury, which is equal to 760 torr, or 1 atmosphere. Okay? These other conversion factors, some of which are on the last page, are you should be aware of, but I would give you those on the exam. Alright, sorry. So there are 4 variables which are needed to define the physical condition or state of a gas. Okay, and these are temperature, which is abbreviated T, pressure, abbreviated P, volume, which is abbreviated V, and the amount of gas, which is usually expressed as N, a little n, which just means the number of moles of gas. Well, the 4 gas laws are equations that express the relationship between these variables, okay, and it allows us to do a number of calculations because of this. First, we're going to talk about the pressure-volume relationship, okay, which was defined by Robert Boyle, okay, and this is called Boyles Law. Boyles Law basically says that P1 V1 is equal to P2 V2. So the pressure of gas 1 and the volume of gas 1 is equal to the pressure 2 and volume 2. Okay, so one thing to think about to really help make this a little clearer is that a weather balloon, okay, is used as a practical application of the relationship between pressure and volume of a gas. Okay, so as the weather balloon ascends into the atmosphere, the volume increases. But as the weather balloon gets further from the Earth's surface, okay, basically the atmospheric pressure is going to decrease. So you can see that the balloon's being squished because the atmospheric pressure is really high down at the Earth's surface, but as it moves away, it becomes, it's expanding. The second law is called Charles' Law. Okay, it relates volume and temperature of a gas. So Jacques Charles discovered that the volume of a gas is going to increase as temperature increases, and that the volume decreases as temperature decreases. Okay, pretty much the easiest example to think of, once again, is a balloon. Right, it's filled with a gas. If you heat that balloon up, right, the balloon starts to expand, and then it's going to pop. Okay, but if you chill the balloon, it starts to shrink up and become all wrinkly and so forth. Okay, so to compare the same substance, the same gas, under two different conditions of different temperature, we can then use the equation that says V1 over T1 is equal to V2 over T2. So basically, if you have a volume of a gas and you know what temperature that's at, and now you say that you increase or decrease the temperature, you can plug that in, solve for volume. Okay, so that's how a lot of these gas laws are applied. Okay, conditions change, and we're still looking at that single gas. The third law we're going to talk about is Avogadro's law. Okay, Amadeo Avogadro realized that equal volume of gases at the same temperature and pressure contain equal number of molecules. Okay, so if we look in this figure, right, we can see that basically if we take 22.4 liters of helium, 22.4 liters of nitrogen gas, or 22.4 liters of methane gas, okay, if we keep that at 0 degrees C at 1 atmosphere of pressure, we can see the mass is different for each of these, but the number of gas molecules never changes. It stays the same. And so Avogadro's law actually relates the volume and the amount of gas. So this law basically states that the volume of a gas at constant temperature and pressure is going to be proportional to the number of moles of gas. Okay? And so to compare volume and moles of a gas, we can use the equation which has V1 over N1 is equal to V2 over N2. So if volume changes from one condition to the other, we can then solve for how many moles of gas that is. Okay. If N is going to be constant, though, then we can substitute back in P1 V1 over T1 is equal to P2 V2 over T2. So really I'm giving you a toolbox of these different equations that you can use relating some of these different properties. So we can actually derive what's called the general gas law or ideal gas law by combining both Boyles' law, Charles' law, and Avogadro's law. And basically we can say that the volume of a gas is directly proportional, which is this little symbol, to the moles of gas times temperature divided by pressure. Okay? But this proportionality constant here, okay, we can actually call R. Okay? And R is just the ideal gas constant. Okay, it has varying units and different numerical values for each of these units. Okay, so it's important that you understand what the units are for both pressure, volume, moles, and temperature. Okay, to determine which R value you're going to choose. I will give you this table in the exam. Okay, so temperature is pretty much always going to be in Kelvin, or you should always make sure it's in Kelvin. And the pressure and volume can have different units, okay? So just keep that in mind. And so basically if we substitute in this this proportionality constant for R, we then get V equals R NT over P, okay? And then we can substitute PV equals nRT. So this brings up the question, what is an ideal gas? Well, we can define an ideal gas as a hypothetical gas whose pressure, volume, and temperature relationships are described completely by the ideal gas equation. Okay? And with this, that means there are three assumptions that we make about an ideal gas. Okay? These are molecules have zero volume, that there's no attractive force between these gas molecules, and collisions between the molecules and the wall are elastic, so they just bounce off one another. Right? The other thing we can keep in mind is that an ideal gas, its standard temperature and pressure, STP, okay, has a molar volume of 22.4 liters. Okay? That's always going to be the case. And we can actually calculate this using that ideal gas law equation. Okay? If we plug in the standard temperature and pressure conditions of 0 degrees Celsius and 1 atmosphere, okay, and then we can solve for the volume, we can then solve, we can solve for that molar volume as well, for 1 mole. Well, we can also use the ideal gas law to define the relationship between density and its molar mass. So previously, back in chapter 1, we defined that density is equal to mass over volume. And we can actually plug that in as density equals mass over volume. We can rewrite that as saying that the pressure is equal, or pressure times the molar mass, capital M, divided by RT is equal to the density. Okay, so you're welcome to go through this derivation in the book, but basically density is just equal to pressure times the molar mass divided by RT. Okay, thus the higher the molar mass and the pressure, the denser the gas is going to be. Okay, we can actually manipulate this equation then and solve for the molar mass, which just is equal to density times RT over P. Okay, and so that allows us to actually calculate the molecular mass of the gas if we have the density and the pressure and the temperature. So many times also we want to know the identity or quantity of a gas in a chemical reaction, and we can calculate the volume of gases consumed and produced in a reaction by using the moles in a balanced chemical equation or a balanced chemical reaction. Okay, and so this is the basic path. If we have the gas data, we have the moles of nitrogen gas, we can then convert that to moles of sodium azide using the balanced chemical equation and then solve for the grams. Okay, last thing is going to be pretty quick. We've been talking about a single gas, okay, but what about gas mixtures? So a gas mixture is going to contain 2 or more different gases. And we can actually determine the pressure of the overall gas mixture by calculating the pressure exerted by a particular component of a gas mixture. And we actually call this the partial pressure of a gas. Dalton defined the law of partial pressure, which just basically said the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. So basically, total pressure is equal to P1 plus P2 plus P3, etc. We can basically substitute in, and basically what we find is the total pressure of a gas is equal to the total moles of gas, RT over V. Well, every gas in a gas mixture behaves independently, right? And so we can actually relate the amount of a given gas in a mixture to its partial pressure. Okay, and so this is just X1 is equal to N1 over N total, which is basically expressing the amount of a given gas is the ratio of the number of moles of one component, N1, and the total number of moles in the mixture. Okay, we call that the mole fraction, and then we can actually calculate the partial pressure of that mole fraction, or that one gas, by just multiplying the mole fraction times total pressure. An experiment that you'll conduct in the laboratory is to measure the amount of oxygen gas released from heating potassium chlorate. And so in this experiment, basically, you have a tube that's connected from the reaction to a water pan and then into an inverted beaker filled with water. So as oxygen gas is produced, it pushes the water from the beaker, okay, into the pan, and then the total pressure inside the beaker is the sum of both the pressure of the gas collected and the pressure of water vapor in equilibrium with liquid water, which we could then use this equation to actually solve for the pressure of the gas, which is oxygen. Okay, if we know the pressure of water and we know the total pressure, we can then solve for that. So this concludes Chapter 10, Module 13, and this online course. I hope you enjoyed this self-paced course. Good luck on the final exam. Let me know if you have any questions.